Looking at section 2.5 on inequalities. Things aren't always equal to each other, so we don't always have an equality with an equal sign. Sometimes we have an inequality. Some general notation, which I'm sure you've seen before. This symbol here means less than. The symbol here means greater than. The line underneath it means less than or equal to, and the line underneath it here would mean greater than or equal to. One way that I know people remembered it is it points at the smaller number. That symbol points at the smaller number. It eats the bigger number. However you want to try and remember which way that sign is pointing, make sure that you keep that straight. Don't worry about those yet. Solving. So when you're solving a linear inequality, we'll start with linear inequalities. You solve it in the exact same way as if you were to solve an equation. If you want to get x by itself, isolate the variable. We'd add 2 to both sides of the inequality. We'd divide both sides by 3. X is greater than or equal to 3. So x could be 4, 5, 6, 7.2, 9.57, or x could be exactly 3. Because there's this extra line here, x could be equal to 3. Solving, again, same idea. We can distribute through the parentheses. We want to get all the x's onto the same side of the inequality. We're actually going to subtract 2x, and there's a reason for that, instead of subtracting 3x from both sides. And I'll come back to why I subtracted 2x from both sides of that inequality instead of subtracting 3x's. I added 12, and I'm done. X is less than 12. So it could be 11, 10, 9.3, 9.57, pi, square root of 2, are all less than 12. X could not be exactly 12. X could be 11.99999999999, but it couldn't be quite 12. Negatives and inequalities. This is one place where you have to be careful with inequalities, where what happens with this is not important with equations. And I'll show you what I mean. So if we solve this, if we just solve it the way we've been solving things, you divide both sides by -5. The correct answer ends up being x is greater than -5. You'll notice that this symbol changed here. Let's pretend I didn't flip that sign around. Let's pretend I left it the same. What would be x is less than -5. If you pick a number less than -5, say -6, if x was -6, -5 times -6 would be a positive 30. And 30 is not less than 25. So it didn't work. However, if we pick a number greater than -5, say -4, -4 is greater than -5. -5 times -4 is a positive 20, and 20 is less than 25. So the only way to make this function, make this work, is if you multiply or divide with a negative number, we're going to flip the symbol around. We're going to flip that symbol over. Instead of less than, it becomes greater than. Really, if you did that with an equal sign, if you divided both sides of an equal sign by -5, and you flip the equal sign around, nothing changes. It's still an equal sign, so it doesn't really do anything. But with inequalities, it does make a difference. All right, graphing linear inequalities. So again, we solved this. I'll go back, to this here. I mentioned earlier that I subtracted 2x from both sides. I did that because I didn't want to deal with negatives. If I subtracted 3x from both sides, I would have had a negative x. I try and avoid negatives simply for the fact that it's one less thing to worry about. Because if you divide by a negative, you have to remember to flip that sign around. If I can avoid negatives, it's one less chance that I'll make a mistake. So I try and avoid having a negative x if possible. So that way I can avoid dividing by negatives or multiplying by negatives. It's going to happen eventually, but if you can avoid it, it just makes it easier. Graphing. Okay, so we've already solved these. I'm going to talk a little bit about graphing. So x is greater than or equal to 3. So I'm going to go to my document camera here. Go. So x is greater than or equal to 3. And sorry, the other one was x is less than 12. Okay, so if I'm going to graph these, we can't list all the solutions to either of these inequalities. I mentioned a few of them before. X could be, for the first one here, x could be 4, x could be 5, x could be 6, but x could be any decimal in between. X could be pi, 3.14159, blah, 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 blah. It's in there somewhere. And so we cannot list all the solutions, but we can graph them all. So the way we graph a linear inequality is we're going to draw a number line. I don't require 0 to be on the number line. You could, but I don't require 0 to be on the number line. But the solution needs to be on the number line. So I'm going to put the solution in front, and I'm going to put a couple numbers on either side. There we go. So there's my number line. It goes on forever in both directions, but the solution 3 is on there, or this part of the solution right there anyways. So then this says x is greater than or equal to 3. So x could be 4, x could be 5, x could be 6, 7, 8, 9. So I'm going to draw an arrow going in that direction. And I would say that x could be anything bigger than 3. Where it gets really close to 3 is where we have to be careful. This says that x could be equal to 3. However, this one says x could not be equal to 12. So how do you say that the line does, well, I'll show you what I mean a little bit more. Let me do this one. So 12, 13, 14, 10. Oh, so I've got my number on there, 12. I've got a couple on either side. This says x is less than 12. 11 is less than 12. 10 is less than 12. But again, we're going back to that idea of how do we show that it gets super close to 12 but doesn't quite equal 12. But this one does equal 3. That's where, actually, I'm going to go back to this first slide here. The open circle versus a closed-in circle. This is going to come back in chapter 5 or chapter 6, I forget, where I think it may be chapter 5, where these open circles and closed circles are going to come back in and come back into play. So an open circle is like a hole. It gets super duper close, but doesn't quite equal. A closed-in circle, we filled in that hole, and it could equal that number. So with these ones, since x could equal 3, I'm going to close in a circle there. And that's how we denote that it could be 3. 3 is a possible solution. Here, 12 isn't quite a possible solution, but 11.999999999 is a possible solution. So we put a hole over 12 to show that it doesn't quite get there. And that's how you graph a linear inequality. Compound inequalities. So a compound inequality could show up in a couple different, or look a couple different ways. We have this one right here. I'm going to show you how to solve this compound inequality. A compound inequality is when you have more than one inequality at the same time. This would be like if you had, let's say you had a pool, a swimming pool. You need to have so much chemical in there to kill all the junk that people put in. So we've got, so you need to have some chemical in there, but too much and you're going to burn people's skin. And so you have to have it in between. You have a minimum amount, you have a maximum amount. You want to keep it somewhere in between. It's kind of like your temperature, your body temperature. You want it somewhere in between a certain range of acceptable temperatures. So that's kind of what we're looking at here. Escape out and move over to the document camera again. The way we're going to solve this is we are going to ignore half of it to start with. Ignore that half. And I'm going to solve this as if that other half wasn't there. So I'm going to distribute through the parentheses. There we go. I get 2x plus 8 minus 5. I can combine some like terms here. So it'd be 2x plus 3. And I'm going to solve for x. So I'm going to subtract 3 from both sides. I get 4 is less than 2x. Divide both sides by 2. Sorry about that. Okay, so we solved it. X is greater than 2. 2 is less than x. Now, let's go back here and look at this side. See if this works. So now we're going to do the same thing, except we're going to solve it with the 13. So we're going to solve it on the right side. Again, distribute through, combine like terms. We'll subtract 3 from both sides of this inequality. 10, divide both sides by 2, and I get that x is less than or equal to 5. My compound inequality then, for my original inequality, solving for x is somewhere, any number that's greater than 2, that's also less than or equal to 5, will meet this piece here. So if you pick a number 3, 4, 3.2, and you plug it into this original equation, or inequality, excuse me, you will get a solution that's between 7 and 13. So that's how you solve a compound inequality. You solve it the same way as you would any other inequality. You just do it twice, basically, one to the left, one to the right. Give this one, actually I take that back. I'll show this one. And so that first one, we solved it as if it was in between, which it is. You could also see an inequality like this. Negative 4 plus a is greater than 1, or negative 4 plus a is less than or equal to 3. This is a slightly different situation. We're not trying to find a number in between a certain range. It could be bigger or less than a certain thing. So solving that is going to be done in kind of the same way. So I put that back up. Here we go. So if we're solving that, we're really just going to solve each one separately. We've got negative 4 plus a is greater than 1, and we've got negative 4 plus a less than negative 3. So if I go back over to my document camera here, that's an a. If I add 4 to both sides, because again, negative 4 plus 4 is 0, so that's kind of the point, just to make that a 0. Get a could be greater than 5, or add 4 to both sides here, a could be less than 1. That would be my solution. Any number less than 1 will work for whatever game I'm playing, and any number greater than 5 will work for whatever game I'm playing. So an or, you're just going to solve them separately. This first one, you could almost do it as an and. It has to be greater than 7 and less than or equal to 13. This one has to be greater than 1 or less than negative 3. Okay, I'm actually going to pause it here. I'm going to do a second video on quadratic and rational inequalities.